Okay, let's look at some other problems to help us review for our final exam. Now, most of these problems come from Module 6, which is on the exponential and the logarithmic functions. So this first thing says, are the functions f of x equal x squared minus 5 and g of x equal square root x plus 5 inverse functions? Now, two functions are inverse. Do the composition f of g of x. It is the exact same of g of f of x. So if we compose them both ways, and they both just equal x. So if I start by doing f composed with g of x, that would be putting g in for f, so that's going this way. So I get there. And then it would be minus 5, because I'm putting that in. Now the square and the square root will cancel, so this just gives me x plus 5 minus 5, which will just give me x. So that way is good. That way it does turn out to be x like we wanted to. So now we have to do it the other way, g composed with f of x. This means we're putting f into g. So if I put that in, I have the big square root, and then I have x squared minus 5 I'm plugging in, and then plus 5. Now these will cancel out, so I'm just left with the square root of x squared, which is just x. So it works out both directions to give me just x. So because those are both x, we can say f of x and g of x are inverses. Alright, number 2, does the function represent exponential growth or decay? Well, growth is when something, keeps growing, keeps getting bigger and bigger and bigger, and decay is when it goes down. Now, it's really easy to figure this out. I mean, you could graph it, because we could see that growth exponentials go like this, and decay exponentials go like this. So you could certainly graph it and see what it looks like. But really, you can figure out whether it's growth or decay by this number right here. So if that number is, we call it the base, if that base is greater than 1, then it is growth. If that base is less than 1, but of course still bigger than 0, then we have decay. So since the 4 is definitely bigger than 1, we have growth, so this would be a growth. And it should make sense because you're taking 4 to higher and higher power, so that would get larger and larger and larger. Okay, let's look at number 3. 3 says simplify the logarithmic expressions. Now simplifying the logs, there were a couple rules. We'll kind of rehash those right here. The 3 rules for logs that were the main ones said if we had log of A plus log of B, then I could rewrite that as a single log of A times B. We said if we had log of A minus log of B, this could be written as the log of A divided by B. And our last rule said if we had a number in front of a log, so n log A, then I could bring that n up and I could write this as log A to the n. So we can use these rules to kind of simplify some logarithmic expressions. So if you look at the first one, we have log of x plus log of y minus log of z. So if I look at just the first two, we have 2 logs added together. So log of x plus log of y will be log of xy, because I just multiply them together because they're added logs, minus the log of z. Now from up here we know the subtraction of logs means division, so to write this as a single log, it would be log of the first stuff, which is xy, divided by the second stuff. So I can simplify that expression to log xy over z. Okay, B is very similar, except for we have the exponent, the number in front, so I can actually start by taking that up front as an exponent. Now I can rewrite this as log base 4 of x, so don't worry about the 4, it's just kind of there as the base, minus log base 4 of 2 to the third. But now similarly we have the subtraction of logs, so I could write this as log base 4 of x divided by 2 to the third. 2 to the third, 2 times 2 times 2 is 8. So that expression would simplify to log base 4 of x over 8. Okay, number 4 talks about solving the equation by converting forms, round to the nearest hundredth when necessary. So if you remember when we had the log and exponential forms, we said the exponential form, b to the x equals y, could be converted to log form, where it would be log base b of y equals x. So this is that rearrangement formula where you have an exponential form and you have a logarithmic form, depending on what you need. The nice thing about the logarithmic form is you get your exponent all by itself. So in this first one, on A, it says 2 to the x equal 8, so we want to find what x is. Now this is in the exponential form, so I can turn it to this log form. So this will be log base 2 of 8 equals x. So the x is by itself now. Now if I was going to put this in the calculator to figure out what log base 2 of 8 is, recall how we do that. We write log of 8 divided by log of 2. So you actually write both logs and you divide them. And so this would just give us 3, just from the calculator, so x equals 3. And that was a pretty easy one, because if you think about it, 2 to the third power, 2 times 2 times 2 is 8. So that would make sense. Alright, let's look at B. 3 to the 3x minus 1 equals 7. So again, this is an exponential form, so I'm going to turn it to log form. So this would be log base 3 of 7 equals 3x minus 1. So we have a little bit more of an equation to do this time, but we first will have to figure out what is log base 3 of 7. So to do that, I would do log of 7 divided by log of 3, because that change of base formula, which was what it's called, will help us approximate what that log is. So rounding to the nearest hundredth, this log would be 1.77 equals 3x minus 1. So to solve that, I would add 1 to both sides. So 2.77 equals 3x, and I would simply divide by 3. So x is going to be, rounded to the nearest hundredth, 0.92. So solving these exponential and log equations really just comes down to being able to change between the exponential and the logarithmic form. Okay, let's look at C. C is a log equation. It says log base 3 of 7x minus 12 equals 2. So I'll change this to exponential form. So this is 3 to the second power equals 7x minus 12. And again, I'm just following that formula at the top of the page for conversion. So 3 to the second is 9. 3 times 3 equals 7x minus 12. I will add 12 to both sides. So that's going to give me 21 equals 7x. Divide by 7, so x is going to be 3. So solving these logarithmic exponential equations definitely going to be something that will be on the exam. Okay, number 5 is talking about a word problem. The number of quality math teachers in America is declining. The number of teachers declined at a rate of 8.7 per year from 189 quality math teachers in 1980. How many will there be in 2030? Well, this goes back to when we had two formulas. The amount, y, in any growth or decay equation is A, where this is the initial amount, how many we start with, times 1 plus or minus the rate. It's plus if it's going up, it's minus if it's going down, to the t, where t is typically the time. So in our problem, the number of quality math teachers is what we're trying to figure out. So I'm going to make y the number of quality teachers, and I'm going to make t the number of years since 1980. Because everything in this problem is based on 1980, because you can see it starts in 1980. So our equation is going to be y equals A. A is how many we had at the beginning in 1980. That'd be 189,000 times 1 minus, because the rate is going down, 0.087 to the t. Now we want to know how many quality math teachers there are in 2030. Well, 2030 is 50 years after 1980. So essentially we're trying to figure out when is t going to be equal to 50. When t is 50, what is y? So y will equal 189,000, parenthesis 1 minus 0.087 to the 50. And you can simply type this in a calculator and it would tell you the number of quality math teachers in 2030. So I get 1995.26 teachers. Alright, the last one talks about compound interest, which was a different formula, another one you should probably have for your exam. The compound interest formula said the amount in the account is equal to the principal times 1 plus the rate over n, which is the number of times compounded in a year. So quarterly would be our compounded, would be our n, to the nt. So we want to know how much money is going to be in this account. So we want to know A, if we invest, our principal is 1,100 because that's how much we start investing, times 1 plus the rate. Now our rate in this case is 0.039, divided by compounded quarterly, so there are 4 quarters in a year, so over 4, to the power of n, 4 times 12. So really, to figure out how much I have in this account, I'll just put all this in my calculator. So 1,100, parenthesis 1 plus, and just put it right like you see it. Make sure you put those parentheses around the exponent. That can definitely help. So I get $1,752.50. All right, so hopefully this second part of the review is helpful to kind of review our exponential equations.